this computer. Okay, so we are recording. Now, there was a question about accelerated frames of reference. Is that what you were saying?
Yeah, just the idea of accelerated frames, and that like the frame is moving, but you're not moving. Maybe that is confusing a bit.
Yeah, and you said there was a specific question. You said it was question 3 on what assignment?
Yeah, on the packet of the recitation questions.
Oh, the scenarios.
Yeah.
Oh, the one in the spaceship?
Yeah, but today, don't know, it seemed that it's a bit different, the question, or maybe I just didn't get it. Like, I think Walter mentioned that like the people are moving. I mean, it's like an elevator moving upwards, something like that.
Well, a person in the spaceship, right, would be moving. Like they're not fixed in place. They can walk along the spaceship, so they can move. But the frame that they're in, the spaceship, is moving, right? So it's not fixed, and there is an acceleration, which is centripetal, right? It's going around in a circle. So there is an
Yes.
acceleration to the people in here, but I'm not sure exactly what you mean by there's more
Okay,
to
yeah,
it
because
than that.
yeah, I mean, what I got from it is just like Fn is going inside always.
Right.
Just right, like, and that's the centripetal force. That's what I understood, but maybe just today I got a bit confused. But I guess, yeah, I guess it's okay.
Yeah, I mean, when he was saying that it's an accelerated frame, it just means that like the object that they are in is also moving, or rather, it's accelerating. Sorry, I'll look at the chat. If there's somebody here for PHY 212, go to group room 1. Sorry, I just realized that there were messages here. I'll read those in a second, but to finish what I was saying is you've got, this ship, and I know he didn't draw it like this, but imagine the ship is like a donut and it's like turning and the people are here. The people can move in the ship, but the ship is accelerated because it's going in a circle with a constant speed, right? I mean, if it didn't, it would be kind of weird, because then if the speed was always changing, it would be difficult for people to walk. So you want to have a constant speed as you're going around in a circle, but in order to do that, you need to have an acceleration, correct? And that acceleration in this case is centripetal acceleration.
Okay, yeah, that makes sense.
Yeah, and
Thank
then
you.
by definition, this is an accelerated frame, correct? Okay, somebody said something about, I think Walter was talking about how since there's no gravity, they move up due to Fn. No, what he's saying is if a person is standing here, right, the normal force is always perpendicular to the surface that they're standing on, so it points in this direction. If they're standing here, did that backwards. The normal force is in this direction. If they're standing here, normal force, the direction is always towards the center or upwards to them, right? Because if you're here, this is above you. If you're here, this is above you. So it's upwards, but really it's towards the center. Any other questions about that? Okay, so in that case, who wants to ask a question? That's what we're here for. Not everybody all at once, though.
I guess I do have another one. I just don't want to talk a lot. I'll just ask real quick. In the third question on the homework, I'm just trying to understand the difference between the third question and the seventh question.
Which homework?
And like how the third question on the homework, just
Which
like
homework?
drawing the, oh, sorry, homework 5,
Gotcha.
question 3.
Okay, in this exercise, you will think carefully about the meaning of our constant g, so the acceleration. Recall that the scales measure the normal force they exert, and the apparent weight of an object is the normal force on the surface below it. For this exercise, use the standard value of g. Later, we'll see how this is not quite. I'm assuming he meant to write South Pole, not North Pole. On the South Pole
Yeah.
of the scale read, suppose he stands at the equator and stands on the scale there. What is the angular acceleration? Remember, the Earth is rotated on its axis at an angular velocity of 1 rotation per day. You will need. Okay.
Yeah, just if like drawing the force diagrams at the North Pole, like or South Pole versus the equator. Just wanted to ask about that.
Okay, so when you're talking about standing on a sphere, sort of like this, it's a really shitty picture, I'm sorry. All right? Whether you're here or here, right? Is that what you're saying?
Yeah.
Okay, so what are your free body diagrams here?
On the top one, it's Fn going up and mg going down. But I'm not sure how to draw the one on the equator. Like, is it a person that I actually drew it on the other side? I drew it on the right of the page. Doesn't really matter, but like not 3D.
Like here.
Yeah. So is the person like, where is his head? Is it like, still it's hard for me to picture where's top and where's his bottom?
Well, I mean, if you are a person on this part of the earth, you are standing like this, right?
Okay, so Fn is going actually to the right and mg is going inside.
Exactly, because the force of gravity is radial, right? It points towards the center, right? Earth pulls us down, but it's pulling us in. If there was nothing for us to stand on, we would just fall, right? Like if you walk off the edge of a cliff, you're just gonna fall down until the cliff ends. So it's radial towards the center. So yeah,
Okay,
so the free
yeah.
body diagram is the same. The free body diagram is the same.
Yeah, because there's no friction or something. Okay, so I guess the difference between this picture and the in question 7, where it's like horizontal, that's because it's on a merry-go-round. It's not like on Earth.
Right, but here there's actually a difference between the two things that I drew. Between 1 and 2, I wrote Fn minus mg applies to both of them, but there is one difference. What is ma when you're right here? If you're just standing.
Like, first of all, like, what is the positive and negative of the frame? Like, where is positive or where is negative?
So for a person here, they're standing like this, right? So this is plus y, this is plus x, but they're standing on top of the North Pole, right? They're standing on top of the North Pole. What is their acceleration if they're just standing there?
0.
Yeah. So then Fn equals mg. So your apparent weight is your mass times g, the acceleration due to gravity. What about a person that's here? What's their acceleration?
The centripetal.
Exactly, right? So your ma is not 0, it would be Fn minus mg, let's denote that here, equals the mass of the person times the angular velocity squared times r, where r is this distance here. So now when you define Fn is the sum of your mass times acceleration, the force due to gravity, plus your angular acceleration. So this is how they're different, right? This is 1 and this is 2. Sorry, I keep forgetting to check the chat. I'm so sorry. But did that answer your question there about how they're different?
Yes.
Okay,
Thank
good.
you. Yeah,
So
very much.
let me go ahead and try to catch up with the chat. How will the group quiz be graded? You'll be working with your groups. If you're in person, you work in person. If you're online, you work online. And you're gonna either turn it into your TA or you're gonna submit it on Blackboard. Somebody says centripetal acceleration is 0 at the pole. That's correct because the axis of rotation is here, right? If you're turning this way, then a person here is not away from the axis of rotation. So R would be, R would be 0. So this term would be 0. But that's, fine. Here you are away from the axis of rotation. Good. Somebody said acceleration is negative. What was that in response to? Because when you say that acceleration is negative, I include that here in the fact that this is minus mg, not plus mg. As for the value of g, you can use 9.8 or you can use 10. That doesn't really matter. If your answer is 10 or 10.12, it's not a big deal. Okay. So I guess I don't really know what's the best way to label this. I'm writing random numbers. So I guess I call this number 3 from Friday's recitation. So that's, from 323 recitation. This is number 2 is number 5, 3.
This is number 3, yeah. Homework 5.
Okay. What else? There's quite a few of you, so I'm assuming that there are some questions about how to do some problems. Oh, can we look at question 5 from homework 5? Okay. Yes, homework 5 from homework. So gladly we can, so number 3 is going to be number 5 from homework 5. And who asked that? That was, yes, Cole, this will be on the YouTube channel. So that was Emery's Adams. Okay, so let's set up our scenario here. We have a vertical wire or like a metal rod or whatever, and then you have two rods coming out of it, or 2 wires sticking to a ball like this. And they tell us that this angle here is 30 and that this angle here is 60. And that this length here is 1 meter. My picture is clearly not drawn to scale. If you want to look at a better scale, look at the picture on the problem. They tell us,
I think it's supposed to be 60 and 60.
Yes, you are correct in saying that. I think that was Kelly.
Yeah.
Yes, so it's 60 and 60. I don't know where I got 30 from. This is 1 meter and this is 3 kilograms. And that's all the information we have about the problem. They tell us, what is the tension, or what is the speed for what speed is the tension the same? So what is the speed if T1 equals T2? B, what is it? What is T? Okay, so any ideas? How do we start this problem? Oh, this is also rotating. That's how, it's moving. Any ideas at all? How do we do this?
We can find the angle.
You can find the angle?
Yeah.
Of what?
So we can find the one on the inside will be 30, because we know that the whole thing will be 90. So now to find the other one, we know the whole thing will be 180, so it will be 120.
Good.
So the other one will be 30, the one on the top of the triangle.
The one on the top of the triangle. Do you mean like?
Yeah, like if that was a triangle, yeah.
Which it's supposed to be. I just didn't draw very well. So this is 30. Good. Sure.
And then the other thing that I try to do is I try to find R. I mean, I know there's like two R's in a way. So I drew like another triangle. Yeah, one on the bottom and one on the top. I tried to find the other angles, and then through sines and cosines, I tried to find the R's, but that's where I stopped.
Okay, that's a good start. That's a good start because identifying R is really important. So that's a good way to start it. Does anybody have any clue how to find R here? It's actually quite simple. You can make it complicated, but it's actually quite simple.
We can say that the angle there is 90, so the other one would be 30 again. And then just say that the sine of 60 would be the opposite of the hypotenuse. I'm not sure.
What would be 30? You mean here?
Or
you meant
so
here?
you have like a small triangle. Yeah.
Okay, I mean, if you did that, which yeah, you can do that. You can say that this is 30. You can say what? Cosine, you said?
Yes, and then use the cosine, but also I saw on the chat, they say that that will be 1 meter. Now, I don't know the geometry to prove that. Like, I don't remember how you do. I think it's with similar triangles or something, but I don't remember.
Yeah, there's a very simple way to do this, and I'll just say it to you because I mean I didn't even like really think about this. This is an isosceles triangle here, right? 30, 30, 120. Forgetting these angles here, forget this part. Let me actually make this a better line. Oh, wow. This is a 30-degree angle. So if this is 1 meter, then this is also 1 meter. All right. Then, as you were saying, this is 60. This is 30, correct? And you know the hypotenuse. So now you can do what you were saying. You can say, I don't know, you can take anything. You can say, you were saying cosine of what? Of which angle?
I said sine, but I think any of them works.
Right, anything will work, right? You can say sine of 30 is going to be, actually, we want the adjacent side, right? So let's use cosine. We want this measurement here, right?
Oh, yeah.
So let's say cosine of 30 is, there's going to be r over 1, right? Where 1, oops. There you go. Fair enough.
Yeah, okay, I got it.
Any questions about how we did that? We just said
So
that.
my thing is, do we have to like write something down for the hypotenuse being 1 meter? Like,
Yeah,
the
you should tell me where
geometry?
that came from. You should tell me where that came from. You could, you can literally just state this triangle equals isosceles, right? You don't even have to spell the word isosceles, right? Because I don't know how to spell it off the top of my head. Therefore, the two sides making a 30-degree triangle, I mean a 30-degree angle, are equal. Then, literally that's an explanation right there. That's a justification as to where you got the number 1 from. If you just throw in a 1, that's not going to earn you full credit because you need to explain where that number comes from.
Oh, okay, thanks.
No problem. Okay, so cool. So we found R, but that's only half the battle, right? What do we do next?
Would you draw out like a force diagram? And I think the only two forces would be like tension 1 and tension 2 going up and to the left.
I agree with you that we should draw a force diagram. So let's do that. Let's we have a ball. Let me actually do it here. You have a ball. And there are, you said two forces acting, tension in this direction. And then there is tension in this direction, right? And I'm kind of estimating with my drawing here. It's the best I can do. Tension 1 and tension 2. Anything else acting on this mass?
And then probably just gravity, right?
Correct. You call it mg, right? Now, at this point, you're free to say, hey, this question wants to know what's the speed if t1 equals t2. So we can just draw out the subscripts and call it t. Cool. So you've done, so I would say that for this problem, step 1 is to draw the picture that we did here. Wait, why isn't this on here? Draw this picture and find R. That would be step 1. Step 2 is draw a free body diagram. So step 1, this is step 2. What's step 3? What do you usually do after you do a free body diagram?
Convert it to the Newton's laws.
Right, Newton's laws, right? So you want to say that the sum of the forces along x equals something, and the sum of the forces along y equals to something. Cool. Thankfully, we know a thing or two about these angles, right? We know that this angle here is 30. This angle here is 30. And we know then, what's this angle here? Or
30 also. 30 degrees.
30, correct. So that would be 30. And this up here is 60, right? As we know from here. 60. So this must be 30. And you can use whichever indication is useful for you. So then what are your forces along x? And also we're going to be using this as our coordinate system. Up is, oh, this should be a y. And this should be an x. I don't know why I did that. So up is positive and to the right is positive. So in that case, what are the forces acting along x?
Cosine t equal to ma.
So you said cosine, so t cosine of what?
Theta, 30 degrees.
30 equals what?
Equals ma.
Well, you're forgetting something here, right? How many forces are pulling the ball to the left,
okay.
to the right? There's two of them, right?
Yeah.
And it's pulling to the left. So we should really call it negative. So this should be t, it should be a minus t cosine 30, right? And then this one, so that's this one here, right? This is why I wanted to keep the T1, T2 notation at first, but it's easier to just drop it. T cosine 30. What about this force here? You know what? Let me trace back my steps. I am going to call them different forces. Even though they're both the same, I'm going to call them T1 and T2, so writing the equation is easier. So this is T1 cosine 30. What about T2? Is it negative or positive? It's to the left, right? So it would be negative. Negative T2, is it sine or cosine?
Sine theta.
Exactly, sine of 30. Right, because this is the opposite is going to be parallel to the x-axis. And that is going to be equal to max. So mass times acceleration along the x-axis. Now, what about for y? You can tell me the equation for y. So T1 and T2 both point up, so they're positive, correct? Well, it's going to be the opposite of these. So it is going to be T1 sine of 30 plus T2 cosine of 30. Here we have the equation set up for the system. Now,
Also have to subtract gravity from the y
oh,
equation.
yes, sorry. I completely forgot about that. That is very good. And you subtract because it's going down and the other forces were going up. Good catch. Okay, so now what? Can we say anything about the acceleration along x or along y? Yes, so the acceleration along y is 0. And that's obvious because if you can imagine that this ball is going around in a circle like this, you know, if you had a ball going around like this, the height doesn't ever change. So the only acceleration that it has is the acceleration along x, which, because it's going in a circle, we can call the centripetal acceleration. All right, give me just a second. My dogs are about to bark. So as we were saying, because it's the acceleration going around a circle, we can call it the centripetal acceleration. So we can reduce our top equation to T1 cosine 30 everything's okay. Sorry, 1 second. Anyway, T1 cosine 30 minus T2 sine 30 equals m omega squared r. Actually, the question says it wants to find the speed and not the angular velocity. So I'm going to write this as v squared over r. They mean the same thing, but now I know that this v quantity is something of interest. So this is equation 1. What about equation 2? Well, T1 sine of 30 plus T2 cosine of 30 minus mg equals 0. It's equation 2. What can we do next? You can factor out t, but now I would actually say, now we can, instead of writing T1 and T2, we can just write t and reduce two variables into one. So I'm literally gonna go back here and say bye, 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 bye. What do we want to find? Well, we want to find the speed when the tension is the same. So solve for V, right? So T, like you said, factor out a minus T, cosine of 30, plus sine of 30. Right? Solve for V. And that part is all you. That's just isolating the variable V. That's all it is to this question. In order to actually solve this, you need to solve for T. Well, you can solve for T using the bottom equation here, equation 2. If you factor out T using equation 2, you're left with sine of 30 plus cosine of 30 minus mg equals 0. So T equals mg divided by sine of 30 plus cosine of 30. You know the mass of a ball, you know what G is, you know what sine and cosine of 30 are. And you've solved the problem. Any problem that involves using forces, you should follow this setup. Draw the picture. Draw your free body diagram. Newton's laws. And then from there, once you get to here, you just solve for whatever variable is of interest. That's it. That's it. And that is everything there is to question 5 from homework 5. But are there any questions about this? Did I skip some steps or confuse anybody anywhere? Good. Let's turn on our lights here. Come on, come on. All right. No questions about question 5 from homework 5. So what's next? What else do we want to talk about? So far, we've gone through 3 problems. Let me separate them. I'm gonna separate this together because it's kind of hard to separate that. This is the end of question 3. Now let's talk about, is that a v squared in the equation? What is that a y squared in the equation? Where is there a y squared? Do you mean this? This is a v. Because remember, this was centripetal acceleration. AC equals v squared over r. No problem. Can we do scenario 8 from the recitation?
Wait, I have a question.
Sure.
Wait, so for 5, do we like sub in the equation we find for t, like for v or something?
Yeah, so you solve for t here, and then this
Well,
is a number, right?
Okay, so you get like an actual number from that, and then you can set that into v.
Exactly, because m is going to be 3, g is going to, so it's going to be literally 30 over 1/2 plus square root of 3 over 2. So there's going to be literally like 15 or some number close to that.
Okay.
And then you're just going to take whatever tension is, plug it into here. Because once you solve for v here, you're going to have, v is equal to this multiplied times r divided by m, square root of all that.
Okay.
Yeah. So in general, when we're talking about these forces problems, you're going to end up with 2, maybe even 3 or 4 equations, probably not more than 3. And you're going to want to solve each one. And then 1 gives you a number that you plug into 2, and 2 gives you a number that you plug into 3. And that's how you solve the whole system. What is K? K is just a constant because I don't know what mg over, I don't know this number off the top of my head. I know that m is 3, g is 10. So this number is 30. This number is 1/2 plus square root of 3 over 2. Square root of 3 is like 1.4 or is that, or 1.7. And this is 2. So, it's hard to do this math in my head. So I'm just going to say this is equal to some number K, plug it into here. No problem. But does this problem make sense? This is a very good candidate for the kind of problem that you might get, because it tests you on understanding centripetal acceleration and centripetal forces. It tests you on doing Newton's laws, because you have to, draw free body diagrams, and you have to solve a system of equations that, it's not like it's not complicated, but it's not kind of given to you outright. Okay, so far so good. Somebody asked about scenario 8 from the recitation, and then we can do homework 5. Question 8, it's not really even a question, right? It says you have a ramp with a small friction of a small coefficient of kinetic friction mu sub k, and it's elevated at some angle theta. So it's saying the following. So this would be question 4. Question 4, number 8 from 323 recitation. I'm labeling this so I can send this to the whole class so that you can review it. Yeah, we can look at both of those. So the scenario 8 from the recitation says you have a ramp with some angle of elevation, it's elevated at some angle theta. An object is pushed up the ramp. So you push the object up, it reaches the top with some velocity, it slides up. Also, an object is pushed towards the ramp. Oh, here you go. Sorry, let me redraw this here. Let me move this over. There's an object here. It's pushed towards the ramp. Once it reaches the ramp, it has some velocity. Now it's here, right? It slides up, and then it's going to come back down. Now, this scenario doesn't really ask you anything, but it wants you to understand that, here, the box is moving with some velocity. It's going to hit the ramp and it's going to go up. What are the forces on the ramp, on the box on the ramp? Who can tell me what the forces are on the box at this point? There should only be 3 of them. Because at this point, you've pushed it and you let it go and it's going to go up. Gravity, yes, so there's gravity. There's normal force, so Fg. There's normal force. And there's friction. What kind of friction? Kinetic friction, because it's sliding. So you would have, let me erase this arrow so I don't confuse you. And then you have force of friction in this direction. Good. When the box is going back down, do this in a different color. And let me shift this picture here. When the box is going back down, what are the forces acting on it? Well, they're the same. So you have Fg going down. You have Fn perpendicular to the surface. But now which direction is friction? Is it up towards the ramp or down towards the ramp? It's going to be up, right? And it's kinetic friction. So let's actually just call this Fk. That's all this is really saying. It's not even really asking you any question. It just wants you to make sure that you can do this, that you can set up the free body diagram, that you can do this for the box, right? So this is one of those problems where you're going to want to rotate your frame of reference. And that's pretty much it. There isn't really that much to these kinds of problems. Are there any questions before we move on? Okay, number 5. which is question 1 from homework 5. So you have a ball suspended from a rope of length 4.5 meters. It's pulled to one side and released, and it swings like a pendulum. It reaches at its lowest point a speed of 6 meters per second. So again, step 1 here, it's always going to be to draw the problem. Let me give you a hint. If you ever don't know, yeah, we're gonna do 2 as well. And I think somebody said, yeah, you said, look, can we do question 2? I'm gonna do 1 first because it's first on the homework. If you draw the scenario, even if you get like none of the physics right, you're at least gonna get some credit for being able to interpret the picture. So that's something to keep in mind. Always try to draw what's going on. So you can imagine that this is the ceiling. And there's a rope that's 4.5 meters long. And there's a ball attached to it. You pull it like so. And you know, if we're gonna replicate this picture, you can imagine that it kind of swings like this, right? In an arc. The question says, this thing is 10 kilograms. And at this point, it has a velocity of 6 meters per second. What is the tension in the rope at that point? So how do we begin? I drew the picture. How do we begin?
We need to draw the force diagram again.
Right, that's a good start. So you take the ball, you draw like a point. So let's call it the free body diagram. What are the forces acting on it?
We have tension going up and mg going down.
Good. Anything else?
That's it. What I know.
That's correct. That's it. So what's step 3? What do we do after that?
The system of the equations.
We don't have to bother drawing the forces along, writing the forces along X because there's no force along X, right? This is literally just tension minus mg equals MAY. Now what? What kind of acceleration does this ball have when it's swinging?
And so this should be centripetal again, right?
Yep.
Or...
And you can kind of see here that this is going in like the circular path, right? So you can say that AY equals AC again. So then tension minus mg is going to be equal to M AC, which you can then rewrite as tension minus mg is equal to M V squared over R. So what is the tension in the rope? Well, the tension is going to be mg plus the secondary term. There we go. Are there any questions about
Yeah,
this?
thank you. No, I think I understand.
Good.
Thank you.
Any questions for anybody else? Okay, cool. Going once, twice, 3 times, nothing. Okay, so question 2 from, I'm getting bored of this color. Let's do blue. Question 6 is the one we're doing. This is number 2 from homework 5. Yes, well, I just read the chat. We'll talk about that in a second. So astrologers claim that the positions of the planet can influence events on Earth. In this problem, you'll calculate whether this is possible or not. Which planet's gravity do you think would have the greatest effect on Earth? Venus' orbit is closest, but Jupiter's is largest. Okay, so these seems like some conceptual questions. So rather than tell you the answer, why don't you just tell me what you think? Andrew, do you want to share your thoughts with this or on this?
I already did the calculation, but initially I just kind of thought if something has a really big mass, then it probably has a greater gravitational pull.
Mm-hmm.
So it doesn't matter if Venus is close. If Jupiter is bigger than Venus, then it would have a greater effect.
Well, that is only partially true, but that's a good way to start it. I would use Newton's law of gravitation, and I would write it down, and I would ask myself, well, what are the factors that affect the force of gravity? Well, there's only two. There's the distance between the objects and the mass of the objects. Now, when we're talking about comparing the force, so let's call force 1 the force of Earth, on Earth, due to Jupiter, or was it Saturn? No, it's Jupiter. And F2, the force due to Venus. So let's call this the mass of Earth, the mass of Jupiter, and F2 is going to be, the same gravitational constant, the mass of Earth, mass of Venus over, let's call this R1, let's call this one R2. Why is it wrong to just consider the mass of Jupiter versus the mass of Venus? There's something wrong with that notion when you look at these two equations. Is that the only variable that changes?
Doesn't the distance also change?
Exactly. The distance also changes. So you're right. If the distance was the same, you could say, well, this number is smaller than this number. So yeah, sure, a force 1 has to be greater. But that's not necessarily true, because the force of force 1 changes linearly as a function of m, meaning if this number is 2, versus it being 4, F1 would be twice as big because you made this number twice as big. Like if I put a 2 in front of this, the whole thing, for this equation to stay true, I've got to put a 2 here because it's linear, right? However, if I put a 2 here, I've got to put a 4 here because this radius is getting squared. So there's an inverse quadratic relationship between radius and force. So no, you can't just say one is more massive than the other. You would have to account for their radius too. Now, as far as which one do you think has the greatest effect? Well, I would look at the mass and I would look at the radius and I would try to do some, estimation in my head about which one's going to be a greater effect, but the only way to really check that is to compute each, and you'll get your answer that way. Does that make sense, everybody here?
I was okay for 2A and B, but 2C, that was a little confusing for me.
Okay, so 2B says, look up the astronomical parameters for Earth and your chosen planet. I don't know what it means by your chosen planet. Am I supposed to know that?
Oh, I meant 2C.
Yeah, I was just going over to B real quick because somebody else asked.
Oh, yeah, sorry.
Yeah, no worries. I don't know what it means by your chosen planet, but okay, I'm gonna choose Venus, I guess. What is the closest they ever are to each other? You may approximate their orbits as circles, and you can find all the information you need. Show how you estimate their distance of closest approach. Oh, okay. Well, saying that you make a hypothesis for A and then you calculate it in B, but I interpret B that you want to find what their closest distance is. What is the closest they ever are? Well, I think you're supposed to look up how close they are, so I don't get what this is saying. You may approximate their orbits as circles. You can find all the information you need on Wikipedia.
So for that, I thought I would just see, well, you said Venus, so I would just look up to see like when Venus and Earth lined up and their orbits, because that would be when they're closest.
Right, you can, sure, that makes sense.
And then I just kind of looked up that distance between them at that point.
I mean, so they could line up at two different points, right? When they're closest or when they're furthest. Because if you can think of like one is orbiting, oh, actually, no, I think you're correct. So if this is the sun and this is the Earth, and like, let's say that this is Venus. If Venus is here, then at its furthest point, then it wouldn't be lined up. But if it's here, then they would be lined up. So yeah, I guess that's a good approach.
Yeah.
That'll work. Because you may approximate their orbits a circle and you can find all the information you need. Show how you estimate. Just so I think what they want you to do here is say, the force on Earth due to Venus is equal to the gravitational constant times the mass of the Earth times the mass of the mass of Venus divided by the separation that you want to find, right? Squared. But because the force that they exert on each other is a centripetal force, that's also going to be equal to the mass of the planet of interest. So I guess in this case it would be Earth times the acceleration of Earth, which you could write as omega squared r, and then you can just solve for r here. But I don't know, it's kind of a weird question. But yeah, you just do that and it's pretty simple. Now, what is the acceleration of your chosen planet? What acceleration does your chosen planet impart to objects on Earth? Is this acceleration relevant to anything? I don't even know what that means, but yeah, I'm actually not sure at all what he means by this. I'm gonna have to ask Walter to clarify to me, unless somebody else here knows what this is asking. But
Like when I read it, I thought, does the acceleration of, I guess, Venus have any effect on the objects on Earth? That's what I take it as.
yeah, I mean, I guess you could measure that because the acceleration of Venus is going to be this. It's going to be centripetal, right? So you can define it this way. Right, Lucy. So what you just said is doing this, right? Writing the force and express it in terms of ma, where a is centripetal acceleration, and then seeing whether, you know, or better yet, you can toss out this term and say, you know, the force is equal to mass times omega squared r. You know, is the force a large number? If the force is a large number, then there is an effect on you due to the angular acceleration of that planet. But if the force is a small number, which it is, then yeah, then it doesn't affect anything at all. Okay, somebody asked, can we go over the difference between v squared r and omega squared over r? I think they meant to say, omega squared times r versus v squared over r. So sometimes I've been writing it one way, other times I've been writing it the other way. And that's because the linear velocity of an object going around a circle is the angular velocity times the radius of that circle. So like when you think of a car tire, like going around in a circle, you know, it's got some rotation, right? And that rotation is what propels your car. So if you know that your angular velocity is, I don't know, 200 revolutions per minute. I don't know what a fast revolution per, let's do 2 revolutions per second, which is pretty slow. Then the linear velocity of your car is going to be 2. So you would have to convert revolutions per second to radians. So 1 revolution is 2 pi. So this would be 4 pi radians per second. Times the radius of your wheel, which, you know, in a typical car, it's about 16 inches. So we could just say that, I don't know how many meters, 16 times 2.5, 32. Let's just say it's about half a meter. So this would be 2 pi meters per second. So that would be your linear velocity. So I can go back and forth between this and this, because when I define my centripetal acceleration as v squared over r, I can also then say AC is omega r squared over r. Then I've got omega squared times a single r. I forgot who asked that question. I think it was Zoe. Does that help your question?
Yeah, that makes sense.
All right, good. So now somebody asked about question 9 from the group exam scenario, which was, oh, yes. So let me write this as question 7. Which is Q9 from 323 recitation. So a person is standing in a subway looking forward. She's not holding on to anything, trusting the friction between her shoes and the ground to keep her balanced. The car travels straight forward at a constant velocity for a little while, then travels up and over the hill, accelerating downward as it does. It then turns gently enough that the passengers do not slip and fall. Finally, it applies its brakes, coming to a stop. You're interested in the forces acting on her and in the things that she experiences during this process. So, what are the moments of interest then? What do we want to know here? Any ideas? I'm sure some of you must have tried it. So when the person is just standing there on the bus, right? What forces does she feel if the bus is moving with a constant velocity? What forces does this person feel? There's a few dozen of you. I'm sure a few of you must have some idea what the forces are. There's just gravity. Good. So if she's standing on the surface, there's the force of gravity. But because she's standing on the surface, there's also the normal force. Makes sense, right? So when it's going downhill, it accelerates downwards, right? So this is case 1. Case 2, when it's accelerating downward, right? The lady is, say, like this. What's the free body diagram then? Is gravity still present? Yep. So gravity is going to be down. The normal force is going to be in that direction. But now exactly, you're going to have a static friction that's going to stop you from wanting to fall forward. So that gets introduced, right? Now the lady's going down, you know, the bus is like this. So there's the normal force pointing up, there's gravity pointing down, but there's some friction going in that direction so that she doesn't fall face first. Okay, what about scenario 3? Scenario 3 says she makes a left turn. The bus driver makes a left turn. So now you're on flat surface again. The person is standing here. So what does the free body diagram look like for the person as the bus makes the right turn? Goes without saying, mg. And the normal force is still present. What about friction? Is friction present when it's making a right turn or a left turn? Yes, and in which direction? To the left, right? To the left, because you're gonna want to fall to the right. Your body's gonna have friction with the floor that's gonna keep you steady. Scenario 5, bus is coming to a stop. Or sorry, scenario 4. She's standing here. Gravity is still there. Call it FG, sorry. And the normal force is there. So she's, you know, you're standing on the bus is coming to a stop. So it applies the brakes. In which direction is the friction going to be? Seems a little tricky here, right? So it's not going to be in two directions. It's only going to be in one. And it's not forward, it's backwards, right? Because you can imagine that if you're standing on a bus, it's coming to a stop, your body's going to want to go forward. The force that stops you from falling forward is friction. And that means that if it's stopping you from falling forward, then friction must be acting backwards. In this free body diagram, it's like coming out of the page. So, I mean, I guess if she's looking into the page, then the force of static friction would be coming out of the page. if, you know, if it was, she's looking at us, then the force of friction would be going into the page. Does that make sense? So that's all there was to identifying this problem. Essentially, you're always going to have normal force, you're always going to have friction, but you're you're always going to have normal force and you're always going to have gravity. Whenever there is a force that tries to move you in one direction, you're going to have static friction that goes in the opposite direction. So when you were going downhill, there was force of friction going in the opposite direction. Where you were making a left turn, your body wanted to go right, so there was friction going left, and so forth. All righty, what is next? We've done quite a few problems from both homework 5 and the question pool. What about previous things? Do we feel good with forces, with the ramps and stuff like that? Are there any questions about that? I'll give you a few moments to kind of look at your notes or your questions and let me know. Thanks for coming, Nick. Have a good one. Molly, did you go over question 3 from the recitation problems? From Wednesday's recitation problem, yes, we talked about it, right? So you have a person on a spaceship and they're standing here. They feel a normal force that goes towards the center of rotation. So the person's going around like this. They're standing here. The normal force is what makes them feel like there's gravity because you're standing on something that's moving with some acceleration, and that's the spaceship, the spacecraft, as they say. No problem. Are there any particular questions about any of the problems? Like maybe you did them and you were uncertain about a specific part? Sounds like you're all prepared then. If question 4 from homework 5. Okay, so let's do question 4 from homework 5, or at least talk about it. Question 4. So satellites in geostationary orbit revolve around the Earth at the same rate as Earth rotates. So they complete one orbit every 24 hours. What is the altitude of a geostationary orbit? You may measure this altitude from its surface or its center, but tell me which one you are using. Lucy, yes. I have the recording. I have no idea where the recording is even going to be saved to, but yeah, we should be able to upload that so that you can refer to it. And I'll also send these notes that I'm writing down, which they're not so much notes, they're just me writing down what we're talking about. So I guess those are notes. Okay. This is problem 8, which is number 4 from homework 5. So you have the Earth, and you have, you know, satellites that are geostationary, which just means that it stays directly overhead. So it moves at the same rate as the Earth. Like so. The question is, what is the altitude?
So is that basically saying, like that's basically saying like what's the distance between the satellite and Earth? And
Yes, or you
I
can.
do see, or what?
No, go ahead.
And I do see like it says it completes one orbit every 24 hours. So that was like one revolution over time.
Yes.
And that is omega, I think, right?
Yep. So the rev, it's one rev per 24 hours. So let's turn that into rev into what?
2 pi, I think, right?
Well,
Over,
typically we want to convert it into radians per second.
yes.
So to do that, you're right. It would be one revolution over 24 hours. We would say one revolution has 2 pi radians. So that would cancel revolutions. Remember, radians are not reading unit, but we're going to write them anyway. And we want to go from hours now to seconds. So 1 hour has 3,600 seconds. So then omega is 2 pi over 24 times 36 radians per second. I don't know what that number is off the top of my head clearly.
Yeah, let me try doing it. I can't find my calculator, so I'm doing it on the computer. Oh, I think somebody, looks like other people are.
So Lucy, the denominator is 86,400 seconds, right? Is that what you're saying? What about the numerator? So it's going to be pi over 4,3,200. Assuming that what you told me is right, this is what we get?
Yes. Yep.
I'm actually going to just throw it in a calculator so I can get the number in scientific notation. 2 times pi over 24 times 3,600 is 7.
Is it 7.27 times 10 to the 5th or negative 5th?
Right. 1, 2, 3, 4. Yeah, 5 minus 5 radians per second. And that's really slow, right? As far as angular velocity goes, because well, my knee hurts. I mean, if you think about it, what this is saying that is that if it's going one whole revolution, it's only doing, you know, a very small rate, like a very small percent of a radian per second, which makes sense because it takes 24 times 3,600 seconds to go around one whole time. So this is the angular velocity. Cool. This is the angular velocity of the satellite.
It is actively dark in this room.
So that seems kind of slow, right? Getting something that's 10 to the minus 5, but is it slow in terms of linear speed?
No, linear speed would be different.
Right, linear speed would be V equals omega times R, where R is the distance from the center of rotation, and the center of rotation would be Earth's radius. Earth's center. So it'd be the radius of Earth plus however high up it is. Obviously, we can't compute this because we don't know R, but it's something to keep in mind that even though this number looks small, we know that it's actually going really, really fast, right? Because if I told you like, oh, I can fly around the Earth, you know, in 24 hours, you'd say that's actually pretty fast, or at least I would think so. But anyway, that's not what we want to find. What we want to find is how high up it is, right? What is the altitude? So how do we go about approaching this?
Well, I know, isn't it like r squared the distance between two centers of things?
Yeah, between the center of one object to the center of the other object. Yep.
So we would find that.
So are you saying to use Newton's law of gravitation?
Yes.
So Newton's law of gravitation tells us that the force that one object exerts on the other is the gravitational constant times the mass of, let's say, Earth, times the mass of the satellite divided by the radius, or the separation between them, squared. That's what you told me.
Yeah, but I have no idea. I just know that's what I should find.
Okay, so you're close, but we want to do something else. We want to relate this to what? What quantity of the satellite do we know?
Well, we know omega, the angular velocity of the satellite.
Yeah, that's good. And do we know a way to relate forces to omega or to angular velocity or linear velocity? What kind of force does the Earth exert on the satellite?
Oh, gravitational?
Gravitational, which is what?
The centripetal?
Exactly, the centripetal force, right?
Yeah.
So the force of gravity here is centripetal. So we can then say that we can also write that that's the same as the mass of the satellite times its angular velocity squared times r.
Oh, I see. Like F equals ma.
Exactly.
Okay.
This is m and this is a. So again, all we did is we wrote the force is equal to what Isaac Newton told us, which is also equal to ma, which he also told us. He told us a lot of things. But writing this second part in a creative way, not necessarily creative, but in a useful way, can let us solve for something that's contained in this part of the equation. So mass of satellite is irrelevant, as we know, which leaves us with G times the mass of Earth divided by omega squared is equal to r cubed, right? So
okay.
r is equal to the cube root of G times the mass of Earth over omega squared. Now,
Okay. I see now.
Good. So what is this number going to be? This is going to be the separation between the center of the Earth and the satellite, right?
Yes.
That's not what we want to know. We want to know the altitude. So this is going to be radius of Earth plus altitude. We just want the altitude, right? So we got to subtract the radius of Earth from this answer.
Right, because you just want to do like the surface of Earth to the satellite.
Precisely.
Okay.
That would be the definition of altitude.
Okay, thank you.
Not so bad, right? No problem. Yeah. I mean, the problem says don't complicate things. It is really this simple. Like you could do it in a couple of lines. Of course, you got to justify your work. But anyway, somebody said something about question 2 from recitation. Molly, did you still want to go over that?
Yes, please, if you have time.
Yep, we do. So let's see. 9. So you have a question number 2 from 323 recitation. So you have a book of mass M. M on some ramp. It's attached, oh no. It's attached by a string to little m, and there's some angle theta. So I just drew the picture that they gave you. Cool. So this kind of, this problem follows the same structure as this problem. You want to start by drawing the picture. That was step 1. And finding any relevant things. Step 2, draw a free body diagram. Step 3, set up a system of equations. And then step 4 will be to solve the system of equation and find what you need. So we've already done step 1, right? It's already done for you. Now I should state that this question doesn't actually ask you to solve for anything, but this could be asking you, solve for the mass of the falling mass, solve for the mass of the book or the book that's sitting on the inclined plane, solve for the angle at which it starts to slide. You can solve for a bunch of different things. So what you're going to want to do is know how to draw a free body diagram for both of them. So we'll call this the free body diagram for M and the free body diagram for little m. So what does the free body diagram for little m look like?
Well, so on this one, the reason I was confused is because I wasn't sure whether or not you should like tilt the axis. Because if you tilt the axis on one, do you have to tilt it on the other one as well? Or can you only tilt one?
You can do just one of them.
Oh, okay.
Daniel, you're correct. So for the little mass, you're gonna have mg acting down and tension acting up. And what about for the big mass? What are the forces on that one? So Fn perpendicular to the surface. Mg, now keeping in mind that this should be a different m than the other one. So I'm gonna make sure it's a capital M. And you're gonna have tension, which is gonna be in this direction. Oh, sorry, I wrote an M here. I don't know why. This should have been a T. So as I think it was, I don't remember who, I think Molly, you asked. Yeah, you can rotate your frame for the free body diagram on the left, but you don't have to do that for the body on the right. Good question. Is there going to be friction? It says that you know that the coefficient of friction between the book and the surface, which means that there is friction. I didn't even see that part. So friction, friction. Is it to the left or to the right? Well, that's going to depend, right? Is the box sliding down or is it going up? Well, it depends on the mass of this thing. If this is big enough to overcome this friction, then yes. If this is light enough that this actually is pulling it down, it depends. So it's either going to go this way or it's going to go that way, depending on the situation at hand. Completely, it really depends on what they tell you. But yes, that's good thing to keep in mind. And then from there, you would just set up your sum of the forces along X and your sum of the forces along Y. And they're going to be equal to MAX and they're going to be equal to MAY. For the big mass, and then for the little mass, you're going to do the same thing, but there are no forces along X, so you just do Y, which is tension minus mg equals MAY. You know, so you're gonna have some stuff here, and have some stuff here, solve for what you need.
Okay, thank you for going over that.
No problem. All righty, so there was a question about 6 from the recitation. I'm on the wrong page. Okay, so question, switch colors now. If any of you are wondering why I keep changing the colors, that's because I was inspired by Sa from Khan Academy. He always taught using different colors, except he changes the colors within the problem. And I do that often, but I figured for this, I would just, you know, not change it up too much. Yes, this video will be uploaded, Lucy. 10, which is Q6 from 323 recitation. Oh, sorry, I just realized that you had asked me that a while ago. Arkoiku, who asked this? Oh, it was a creation. Okay, so this is very similar to the homework problem, right? How do we start this problem? This time it doesn't give you a picture, right? So step 1 would be to draw the picture. What does this problem look like? I have a poll yet again. Theta here, and I think it's and this is theta. I think they tell you something like that. They give you R now, right? So that's going to be just like this problem that we solved for, one of the first ones that we did, except now they give you R. Now they give you R, so the rest is to set up this free body diagram, set up this system of equations, and solve for the question of interest. It's the exact same problem, except the tension is now going to be different. You know, or they could be different, and then they could tell you to solve for like something with a specific velocity or something like that. So in the first problem we did, the question was, what is the velocity when the tension in the string is the same? You know, this could flip that and say, okay, this is the velocity. What are the individual tensions on the string? Something like that. So again, you're going to have mg, you're going to have tension that way, you're going to have tension this way, T1, T2. Yeah, I mean, I won't go over this problem from scratch again because we kind of already did that. All righty, are there any conceptual things or questions that we want to discuss that's not just like crunching numbers? Any doubts about how to approach certain things? Such as, do I rotate the frame or not for different masses on question 2? Things of that nature. Okay, well, if there are no questions, then I guess I will sign off. If any questions do arise, just send me an email. I will send out these notes to, I guess, the whole class, because it would kind of be difficult to keep track of who's here and who's not. So I'll send these out, or maybe I'll have Walter post them on his website. I'll have Walter post it on his website, and that'll probably be easy for everybody to access. If you were here, you're gonna know what the notes mean. If you weren't here, this would just look stupid crazy. But yeah, I'm glad I was able to help you guys. I will be doing this again over the weekend. And yeah, keep good luck tomorrow. You'll be fine. Best of luck to everybody. Have a good night.